In this video, I'll show you how to use Parseval's theorem in Fourier analysis to evaluate the Debye solid-state physics integral that shows up in any graduate level course in solid-state physics. That integral it also shows up in a host of other places in physics, by the way, and in mathematics. In mathematics, it's closely related to what's called the Riemann zeta function, which we'll also see later in this video. So it's a very important class of integrals, and $1 million is up for grabs if you can solve the Riemann hypothesis to which this integral is tied. Now, the integral itself is the integral from 0 to infinity x cubed dx over e to the x minus 1. The different classes of integrals differ in the powers that you put for x. And for certain powers of x, the problem is completely unsolved as of today. So the first thing we do to evaluate this integral, all the tricks that you learned in your earlier life are completely useless against an integral like this. So you have to learn new techniques to proceed. And those techniques involve Fourier analysis. So the first step is to actually expand this as much as possible using geometric series. And the geometric series formula I have in mind is 1 over 1 minus r is 1 plus r squared, and so on, if r is less than 1. Now, for that to hold true, first of all, you need to have 1 minus something. And here you have e to the x minus something. Also, e to the x is not smaller than 1. So the first thing you need to do is some cosmetics. Let's multiply both the numerator and denominator by e to the minus x. Doing so will give me 1 minus e to the minus x, because e to the x and e to the minus x are natural enemies. So I get dx. Now I'm almost there, because this looks like 1 minus r, because e to the minus x is definitely less than 1 for x bigger than 0, because this the graph of the exponential function e to the minus x looks like this. And our range is only from 0 to infinity, so it's definitely always less than 1. So the geometric series formula applies. So we can do this. Integral 0 to infinity x cubed e to the minus x, and I'm going to write this as 1 minus 1 over 1 minus r. So that's just 1 plus e to the minus x plus e to the minus 2x. It's an infinite sum, so it never stops. And that can be abbreviated, if you like, as x cubed e to the minus x, the sum from n equal to 0 to infinity, e to the minus nx dx. So that's our first preliminary step. Now what I can do is I can take the e to the minus x that's alone outside into the summation sign by appropriately adjusting my range of the summation. So instead of going from 0 to infinity, I'll go from 1 to infinity. And in that way, I've absorbed the factor of e to the minus x. Because if you think about it, if I move the e to the minus x inside, the first term is going to be e to the minus x, and it is. So all I have to do is move all the guests to the other room of the hotel, to use Hilbert's analogy of infinity. Now, one of the important theorems in mathematics is called Fubini's theorem, and Fubini's theorem allows us to interchange the summation sign and the integral sign. If you don't know what Fubini's theorem is, just look it up. I'm not going to spend any kind of time telling you about that theorem. The Fubini theorem is valid under a host of general conditions, so most physics applications or solid-state theory or material science applications, you just have to not worry at all about it. But it's a good idea to go and look at the hypotheses, and I encourage you to do so. Now, once you have this, you have to integrate this. Now, integration of something that is a polynomial function of x times the exponential is actually not very hard to do. You can do this by the method of recursion formulas. So what I will do on the side, off to the side, is set up such a recursion. Let me do this for a more general case. Let Im be the integral from 0 to infinity x to the m e to the minus nx dx. in our case m is equal to 3. By integrating by parts, clearly the u function is going to be that's going to be the dv function. The u function is always something that's easy to differentiate, and the dv function is something that's easy to integrate, which, as a result of which, the future integral is even simpler. That's the second condition to be satisfied. The different derivative of x to the m is mx to the n m minus 1. So du is mx to the m minus 1. And the integral of e to the minus nx is negative 1 over n e to the minus nx plus c, which we won't write. So that's your v function. So integration by parts tells us integral u dv is uv minus integral v du. So u times v means this times that. So I get negative, u times v is this times that. So negative 1 over n e to the minus nx x to the m between the limit 0 and infinity minus the integral of v du. Well, v has already got a minus sign, so that becomes a plus, and then I'm going to capture an m from here and an n from there, so I get m over n, the integral from 0 to infinity, x to the m minus 1 e to the minus nx dx. At infinity, e to the minus nx goes to 0, as you can see from the graph. So that upper limit is 0. The lower limit is obviously 0, because while e to the minus nx is 1, this part becomes 0. So both those limits are 0, and I just get m over n times the integral I m minus 1, because it's the same integral except it's gone down in 1 power. Now if you apply this formula over and over again, I get m over n, m minus 1 over n, I m minus 2, and then m minus 2 over n, I m minus 3, and it goes all the way up to 1 over n, and at the end I get I0. Well, I0 is just the integral of 0 to infinity e to the minus nx dx. The numerator is m factorial. So I get m factorial over n to the power m, and that integral is again e to the minus nx is just that. So it's negative 1 over n e to the minus nx between the limits 0 and infinity. At infinity, it's again 0. And at 0, it's negative of a negative, which is positive, 1 over n. So the evaluation of this integral is m factorial divided by n to the m plus 1. I've done it. So all I've got to do now is write I3. I3 is going to be 3 factorial divided by n to the 3 plus 1, or n4. Pretty nice. So let me put that into my equation here. It's going to be the sum from n equals 1 to infinity, 3 factorial over n to the 4. Now it may seem that you've traded one problem for another. How on earth do you find the summation of 1 over n to the 4 from n equals 1 to infinity? FYI, 3 factorial is 6, so this can also be written as 6 times the integral from n equals 1 to infinity, 1 over n to the 4. This, by the way, is the definition of the Riemann zeta function, zeta of 4. In general, the Riemann zeta function is defined for a complex number s as sum n equals 1 to infinity, 1 over n to the power s, and it's one of the most sacred theorems in mathematics, which has not been proved for over 100 years, and anyone who proves that will definitely live forever in history books. All the zeros of the Riemann zeta function are contained in the real line s equals half. So in the imaginary line s equals half. That's the Riemann hypothesis. One of the greatest unsolved problems in all of mathematics. All right, so once you have the Riemann zeta function, you have to find zeta of 4. Now here's where you can get creative. As though all this has not been creative enough, now we really turn up the creativity knob to get any further. And that is, you have to solve a completely different problem. Let's try to find the Fourier series of the function x squared. let f of x equals x squared on negative pi to pi. From one of your homework problems, and I'm not going to do that for you here, if you solve this Fourier series, you will end up getting x squared is going to be 2 pi squared over 3. That's the a naught over 2 term. So let me just tell you what you're going to get. Your a naught is going to be 2 pi squared over 3. Your an is going to be 4 negative 1 to the power n over n squared. This is just regular Fourier analysis, to do which you have to probably use Euler's trick a couple times and recursions like this. So it's a pretty long process. And bn is going to be 0, obviously, because it's a even function. So if you want to write this out as a Fourier series, you'll write this as a naught over 2 plus the sum from n equals 0 to infinity an cosine of nx. Now this is the traditional Fourier series because the interval is minus pi to pi. So a naught over 2 is that plus the sum from n equals 0 to infinity 4 negative 1 to the power n over n squared cosine nx. So that's your expression for x squared. We're not so concerned about writing x squared as a Fourier series, but rather using the Parseval's theorem on it. Parseval's theorem says the average value of a function squared, squared is inside. It's very important that the average of a square is not the same as the square of the average. The square of the average is always smaller. That's one of the important results in statistics. So this is going to be, by the Parseval's theorem, I'm just going to get a naught over 2 squared plus half of the sum from n equals 1 to infinity an squared. Now let's find the average value of f squared directly. So that's by regular calculus. So by regular calculus, the average value of a function like f squared would be 1 over the interval, in this case it's 2 pi, the integral from minus pi to pi of the actual x squared, because x squared itself is f, and I'm squaring that, so that's x to the 4 dx. And that's going to be x to the 5 over 5. Between the limits minus pi and pi. So that gives me 1 over 10 pi to the 5, minus of minus pi to the 5, that's a plus pi to the 5 again. So I get pi to the 5, pi to the 4 rather, over 5. Because that's 2, and 2 times 10 is 5. 2 divided by 10 is 5, and then one of the pi factors cancels out, and I get that. So we have f squared done the traditional way. Now let's put that here. So I get pi to the power 4 over 5 equals a naught over 2 squared. So when I do a naught over 2, I lose the 2 factor. So I get pi to the 4 over 9 plus the square of this. Now when I take an squared, I'm going to get 16, because 16 is 4 squared, and then I'm dividing it by 2. So I get 8. The sum from n equals 1 to infinity, I'll get negative 1 to the power 2n, which is just always 1. And then 1 over n squared becomes n to the 4. Voila! That is our sought for zeta of 4. Zeta of 4 is sitting right there. So Fourier series and Riemann zeta functions have a very close relationship, and it's very likely that the ultimate person who proves the Riemann hypothesis is also going to be something of an expert in Fourier analysis itself. Now what we have to do is simply subtract pi to the power 4 over 5 minus pi to the power 4 over 9 divided by 8 and multiplied by 6 will be your answer to the integral. So let's find out what this is. That's going to be 2 over, I want to make sure I do this right, 4 threes, that's going to be 3 over 4 times 45 looks like the only common denominator here. So that's going to be 9 minus 4 pi to the power 4, and 3/15s are 45. So I get that's going to be 5 over 4 times 15. Oh, 9 minus 4 is 5, yes. Pi to the 4. Okay, I just want to make sure I did all this right. This is 9 minus 5. I was wondering, that didn't look right. Okay, 4. And then I get pi to the power 4 over 15. That's the famous result, the value of the Debye integral in solid state physics, and it shows up in all your formulas when you take a course in solid state physics. They usually don't prove it though.